Today we're going to talk about independent and dependent probability. In all of our previous lessons with probability, we've been doing just one event, so to speak. We've only been rolling a die one time or drawing a card one time. Today we're going to look at doing more than one thing, and then we need to determine whether the second thing we do is affected by the outcome of the first. If the second thing we do is not affected by the first thing that we've done, that is independent probability. So in our first example, it talks about spinning a wheel 2 times for a particular game. The wheel does not care what you got on the first spin. When you spin again, you could still get anything. You could get that same thing again, or you could get anything else as well. So this is an independent probability problem. The first answer or outcome will not affect the second outcome. So in the question it says we're going to spin this wheel twice, and we want to know what is the probability that we get more than 500 on your first spin and then go bankrupt on the second spin. And in probability problems means to multiply. Yesterday we talked about or as meaning addition. And means to multiply. So what we're going to do is find the probability of more than 500 on a spin. On that wheel, everything marked with A has a higher than 500 value. So there are 8 of those, and there are 24 spaces total. And we're going to multiply. The wheel does not care what happened the first time. We could get the same exact space, or we could get any other space, and anything is just as likely to happen. So, and on the second spin, the probability of going bankrupt, those are the spaces marked with B. There are 2 bankrupt spaces out of the 24 spaces that are still on the wheel. So we multiply these together. You can reduce before or after you multiply. I like to reduce before because it makes the numbers smaller to work with. We end up at 1 out of 36 chance that would happen. Questions? The next problem says a game machine claims that 1 in every 15 people win. Now that doesn't mean like every 15th play is a win, because then you would just stand there and wait until somebody does the 14th and then like push them out of the way and do the 15th, and you'd be guaranteed to win. That would be a bad machine. So 1 out of every 15, but it's random per game. So what happened on one game does not affect the next game. You could win 2 times. You could win 5 times in a row. It's not likely, but it could happen. So each game is an independent event. Whether you won the last time or not, the machine doesn't really care. But on average, in the long run, 1 out of every 15 will be a winner. So what is the probability that we win twice in a row? The first time we play, we have a 1 out of 15 chance. Whether we win or lose, when we play again, we still have a 1 out of 15 chance. And so we multiply that together and get 1 out of 225. So it is not likely that we will win 2 times in a row, but it is possible to win 2 times in a row. Questions? In a survey, 9 out of 11 men and 4 out of 7 women said they were satisfied with a product. If the next 3 customers are 2 women and a man, what is the probability that they are all going to say that they're satisfied with this particular product? Now, in some assumptions we need to make, we need to assume that they're not asking all 3 people at the same time by other people's opinions. So our assumption needs to be that the first person comes in, they ask them, did you like this or not? And then the next person comes in, do you like this or not? And the next person comes in, do you like this or not? So that each person has their own individual opinion and is not affected by the opinion of the person before them. So there are 2 women and a man that are going to come in and be asked the question next. So far, the women are satisfied with the product 4 out of 7 times. So the probability the next woman comes in and says that she likes this particular thing is going to be 4 out of 7. The next woman should still have that same likelihood. regardless of whether the first woman did or did not. And the third customer is a man, and so far the men are running at 9 out of 11. So we'd multiply each of these together. These don't reduce nicely. There's a whole lot of prime numbers in there. So I just went straight to a decimal answer on this one. So I get 0.267. Questions? Question number 4 says, refer to the same survey. If the next 4 customers are all men, what is the probability that at least one of them is not satisfied with the product? So we have a important phrase in here, at least one. That means it could be that one man says he's not satisfied with it, or 2 of them, or 3 of them, or all 4 of them say that they are not satisfied with the product. Yesterday we talked about or as meaning addition. So if we think about the problem this way, we have to calculate 4 different things and add them up. What if 1 man is not, 2 man is not, 3, 4, and all of those options? That's one way to do this, but that seems like a lot of work to calculate the 4 different probabilities and then add them all together. So also yesterday we talked about complement probability, where if there's an opposite situation, we can do 1 minus the opposite. So what is the opposite of at least one of them is not satisfied? All of them are. So the opposite of at least one not being satisfied, because that would be 1, 2, 3, or 4 is not satisfied. So the opposite of that is 0, since there's only 4 customers. So we have 4 men coming in. Each of them, according to the last problem, has a 9 out of 11 chance of liking the particular product. So the probability that each of them says that they like it is 9 out of 11, the 4 times. And then 1 minus that would tell us the chances of 1 or more of them saying that they don't like it. And as a decimal, we get that at 0.552. And that may be kind of surprising, because 9 out of 11 is a good chance of liking it. So we end up almost at a 50-50 that at least one of them is going to end up saying they don't like it. And that seems maybe a little counterintuitive, because 9 out of 11 seems like they should probably all say that they like it. But the more and more customers that come in, the more likely it is that somebody is going to say that they don't like it. Questions? Probabilities are where the outcome of one particular event is affected by the outcome of a previous event. Or our first problem is going to be data, and it's where we limit our set. Okay, so where we limit down our set of data, or where we're doing 2 events and 1 event is affected by the first event. So for the first question, it says that we have the probabilities of endangered and threatened animals in the United States. Part A, we want to find the probability that a listed animal is a reptile. The first thing that it says there, the listed animal, that's our denominator. So how are we going to find the denominator? What does it mean by listed animal? An animal on the list. So how are we going to find out what number the denominator should be? Add up the entire chart. So we want to add up that entire chart. And I got 475. I think. And then the numerator says that a listed animal is a reptile. So what's the numerator going to be? Or how do we find that? Add up all the reptiles, because it didn't tell us endangered or threatened, it just says reptile. So the number of reptiles on there are 35. So we do 35 out of 475. It gives us 0.07, or about a 7% chance. Part B gets a little more specific, and this is where we think about dependent probabilities, that we're narrowing down the field of what we're looking at. It says, what is the probability that an endangered animal is a reptile? So now our denominator is just endangered animals. So we would want to add up just the endangered information. So 59, 75, 14, 9, and 198. And we get 355. And what about the numerator? 14. We're just looking at the endangered information in this one. So we want to limit that down to just endangered. And so 14 out of that 355 gives us about 0.04. Okay. So according to these percentages, 7 and 4, reptiles form a pretty small amount of endangered or threatened species. Questions? We are going to randomly select 2 cards from the deck. We want the first card to not be a face card, and the second card to be a face card. And we're going to do this in 2 different ways. Part A, we are going to replace the first card before drawing the second. So in part A, we're going to draw a card, see if it's a face card or not, put it back in, shuffle up, draw another card, see if that one's a face card or not. Okay. So, what is the probability of getting not a face card? Well, how many face cards are there? Face cards are Jack, Queen, King. So 3 and 4 suits, so there are 12 face cards. So how many are not face cards? There are 40 not face cards. So our probability of drawing not a face card is 40 out of 52. And put that card back in, shuffle it up, pick a new card, probability that that new card is a face card. How many face cards are there? 12 out of 52, because we're still drawing from the whole deck since we put that card back. We can multiply these together, and we get 0.178. It's okay to keep them as fractions as well. I typically just go to decimals on these because they're kind of messy. Part B now says you do not replace the first card. Our first draw is exactly the same. We want a not face card out of the whole deck. Now we need to assume that we were successful in that first draw. So we have to assume that when we pulled out a card the first time that it was in fact not a face card. So then, how many face cards are still in the deck? There are still 12 face cards because whatever card we picked wasn't a face card. So there are still 12 face cards left out of how many cards we're picking from? 51, because we're still holding on to that first card, whatever that first card was. So when we multiply this out, we get 0.181, which is pretty close to the first answer. You should always expect them to be pretty close. Changing our card by just 1 will change the probability, but not greatly. So you should not expect those 2 numbers to be very different. They should just be a little different. Same type of problem again. First draw, we want to be a diamond, and second draw, we want to be red. Part A, if we replace. So how many diamonds are there?
Uh,
13 diamonds. It's one of the suits out of 52 cards. And For part A, we're putting that card back in. So whether we got a diamond or not, whatever it was, we're putting it back in, shuffling up, and now we're going to draw again. And now we want a red card. How many red cards are there? 26 out of the whole deck, because we put that card back. These ones actually reduce pretty nice as a fraction to give 1/8 or 0.125.
Your homework, do you want us to put it in decimal?
Decimal or fraction is okay. For part B, we're not going to replace that card after we draw it. So our first draw is exactly the same. There's still 13 diamonds, 52 cards. But now we're going to assume that we were successful in that draw. So I pulled out of the deck a diamond, and I'm holding that diamond in my hand. And now I want to draw a red card. So how many red cards are there? 25, because a diamond is a red card, and I'm holding one of those in my hand. So there are only 25 left out of 51 left. So we multiply those out, and we get 0.123. So again, slightly different should be expected. Very different should not be. So if you get very different answers, you've probably done something wrong. Questions? The next problem says, you and two friends go to a restaurant, order a sandwich. The menu has 10 different types of sandwiches. Each of you is equally likely to order any type. What is the probability that each of you orders a different type? Okay, so the first person places their order. There are 10 sandwiches to choose from, and they can pick any of the 10. Now, when the second person orders, if their goal is to get something different, how many can they? 9. But how many can they really pick from? 10, because it's not like this kitchen only has enough stuff to make one BLT, right? So just because the first person ordered it doesn't mean the second one can't order it. They could still order from all 10, but if they want to be successful in ordering different things, they should really only pick from 9. And it's you and two friends go out to eat, so we've got one more person that needs to order. What's their fraction going to be? 8 out of 10. We multiply that out and get 0.72. So there's a 72% chance that you're all going to have different sandwiches. Questions? Our last type of problem is called a tree diagram, because we're going to make a picture to organize the information that's going to look kind of like tree branches. So it says the American Diabetes Association estimates that 5.9% of Americans have diabetes. Suppose a medical lab develops a test that is 98% accurate for people who have it and 95% accurate for people who do not have it. What is the probability that the diagnosis is correct for any random person who takes it? So when people take a medical test, it's not guaranteed that it's going to give them a right result. Now, ideally, it's going to, most of the time, give a right result. But for this particular test, it says if somebody has diabetes and they test 90 or 100 people with diabetes, it's going to tell them, yes, you have it. But 2 people, it's going to tell them that they don't, even though they actually do. If they test 100 people who do not have it, or did I say that backwards? Yeah. So if they test 100 people who do not have it, 95 of them it's going to say, yeah, you don't have it, but 5 of them it's actually going to tell them that they do. That's why we do medical tests more than once, because it's not guaranteed that the test is going to give you the right result the first time you take it. So you take medical tests more than once to make sure that you're getting a correct diagnosis. So what we're going to do is create a diagram of this information. Starting out with our first separation of the population is that people can either have diabetes or they cannot have it. And there's no gray area there. You either have it or you don't. You can't kind of have it. Okay? So what % of Americans have it? 5%. 5.9% of Americans have diabetes, so we're going to say 0.059. And since there's no gray area, if they don't have it, that should be everybody else. So that'd be 94.1% of the population does not have it. Our next break is going to be about the test, that either is accurate or it is not. If somebody has diabetes, how accurate is the test? 98%. It says is 98% accurate for people who have the disease. So if they have it, it's 98% accurate and 2% inaccurate then. If they do not have it, 5% accurate and 5% inaccurate. So the question asks then, if I pick any random person from the population, they may or may not have diabetes, what is the probability that the test tells them the right thing? That if they have it, it tells them they have it, and if they don't, it tells them that they don't. So there are two different things that could happen. Either they have diabetes and get an accurate diagnosis, or they do not get a diagnosis. So two different branches meet that requirement of an accurate or correct test. In those branches, we are going to multiply the values. So we are going to do 0.059 times 0.98. And that gives us 0.05782. Don't round at this point. We can round our final answers, but don't round here yet. Multiplied the 0.059 and the 0.98. And then likewise in the other branch, we're going to multiply those values, 0.941 and 0.95. So I said there are two things that could happen that would be a good, correct result. Either they have it and the test is accurate, so that's why we multiplied there, or they don't have it and the test is accurate. So what do we do for ors? Add them. So we're going to add those two answers that we got from the multiplications to find that this test is 95.177 or 95.2% accurate for the general population. Your final answer in terms of judging its validity should be close to the majority of the population. So the majority of the population does not have diabetes, so our final accuracy value should be close to that accuracy value of 95. Okay? It won't be perfect because the rest of the population will skew it a bit. But your final answer should be close to what the majority of the population had. Questions? Our last example, in one town, 95% of the students graduate from high school. Suppose a study showed that by age 25, 81% of the high school graduates had a full-time job. Only 63% of those who did not graduate had a full-time job. So what is the probability that they can select a random student and that that student will have a job at 25? So our first breakdown of the population here is going to be to graduate or not. So what percentage of the population in this town graduates? 95% graduates. So 5% of the students do not graduate. Our next breakdown of the population is going to be job or not. If a student graduates, what is the percentage chance that they will have a job? 81. So that means there's a 19% chance that they won't. If they do not graduate, what is the chance that they will get a job? 63. So there's a 37% chance they will not have a job. Okay, just subtracting out from 100 for all those opposites. The question asks, what is the probability that someone will have a job? So there are two branches that talk about having a job. Either that somebody graduated and then got a job, or somebody did not graduate and got a job. Within the branches, we multiply the values. So we are going to multiply 0.95 and 0.81. And we are going to multiply 0.05 and 0.63. And then we are going to add those together because one branch or the other branch could serve as an answer. So that gives us 80.1%, which remember I said it should be close to the majority of the population. So the majority of the population graduated, so our answer should be close to their value of 81%. Okay. Questions? Okay.